In last class, we have discussed problems in three-phase balanced load. Today, let's discuss three-phase unbalanced loads. First, let's start with three-phase unbalanced delta connected load, which is fed by a three-phase balanced supply. The first step is, for a given phase sequence, the phase voltages are expressed in polar form. Step 2, load impedance in each phase is expressed in polar form. Step 3, the phase current is obtained by Ohm's law. That is, phase current is equal to phase voltage divided by phase impedance. Then the line currents are calculated by Kirchhoff's current law. Let's solve this problem. Determine the line currents for the unbalanced delta connected load of the figure given. Assume the phase sequence to be RYB. Given E is equal to 200 volts. So the given problem is the unbalanced delta connected load. We have to find the line currents for the given problem. It's a given figure. Assume the phase sequence is RYB. The voltage given is 200 volts. So this is the problem, delta connected load. It is called unbalanced because if we see the impedance, each impedance is unequal. So it is called unbalanced delta connected load. This is called phase. This is called phase. This is this one. These are the phases. These are called lines. Current IR, IY, IB are the line currents, whereas this current I1, I2, I3 are the phase currents. The given impedance is the phase impedance. Let's solve the problem. The first step is express voltages in polar form. It's given voltage is equal to 200 volt. We have to express phase voltages in polar form. Voltage is equal to 200 volt. It's given. We know that the three phase voltages ERY, EYB and EBR have the difference in phase angles of 120 degree. That is, EYB lags ERY by 120 degree. Similarly, EBR lags EYB by 120 degree. Thus, the voltages can be written as ERY is 200 angle 0, EYB which is lagging ERY by 120 degree. Mathematically, we can write this EYB is equal to the magnitude is 200, but it is lagging ERY by 120 degree. The negative sign indicates this EYB lags ERY by 120 degree. Minus sign indicates lagging. Similarly, if we take EBR, this EBR is lagging ERY by 240 degree. Therefore, EBR is 200 angle minus 240, which can also be written as 200 angle plus 120 degree. Because this EBR is leading ERY by 120 degree. Therefore, we can write EBR either as 200 angle minus 240 or as 200 angle plus 120 degree. I1, I2, I3 are the three phase currents. It is mentioned here, right? I1, I2, I3 are the three phase currents. These are the phase voltages. I1, I2, I3 are the phase currents. How to find phase current I1? As mentioned in step 2, phase current is equal to phase voltage divided by phase impedance, right? Thus the phase voltage ERY in polar form, magnitude angle form. ERY is 200 angle 0 degree, this one, and the phase impedance is 30 plus J40. I1 is the phase current, phase voltage is 200 angle 0 degree, phase impedance is 30 plus J40. 30 plus J40, if you write this in polar form, 30 plus J40 in polar form is 50 angle 53.13 degree. I1 is equal to 200 angle 0 degree divided by 50 angle 53.13. How to do polar division? Just divide the magnitudes. 200 by 50 gives 4. Then subtract the angles. 0 minus 53.13, which is minus 53.13 degree ampere. I1 is equal to 4 angle minus 53.13. In rectangular form, I1 is 2.4 minus J 3.2. Convert this polar into rectangular, we will get this. I2, the phase current I2 is equal to, I2 is the current flowing through this phase. this phase is between Y and B. Thus, the phase current I2 is phase voltage EYB divided by impedance 8 minus J4. EYB divided by 8 minus J4. EYB is equal to 200 angle minus 120. That is EYB. 200 angle minus 120 divided by 16.13 angle minus 60.3. This is the polar form of 8 minus J4. So when we divide, we get this one. Polar form, rectangular form values of I2. We have found phase currents I1 and I2. Next one we have to find I3. I3 is the phase current in the space. Therefore, phase current is equal to phase voltage divided by this impedance. Phase voltage, this phase is connected between the points, that is B and R. Thus, I3, phase current I3 can be obtained by dividing EBR by 15 plus J12. EBR by 15 plus J12. EBR is equal to 200 angle minus 240 divided by the polar form of this one is 15 plus J12 is 19.21 angle 38.7. If you divide, you get this. If you want, you can convert this polar into rectangular form. Thus, the phase currents I1, I2, I3 have found. Next one, it's asked to find the line currents IR, IY, IB. Therefore, we have to find the line currents now. How to find line currents? Step 3 is finding the line currents from the phase currents using Kirchhoff's current law. The line currents are IR, IY, IB. I have to find now the line current IR. For finding this IR, we have to apply KCL at this point. If we look into this point, IR is the incoming current, I3 is also incoming current, I1 is the outgoing current. Thus, IR plus I3 is equal to I1, or IR is equal to I1 minus I3 by KCL. We have the rectangular forms of I1 and I3, just to substitute here. If we subtract this, we get IR. The polar form of IR is 13.53 angle minus 86.5 degree ampere. Next, find IY. IY is the line current. How to find IY? By applying KCL at this point. What are the incoming currents to this point? IY is the incoming current, I1 is the incoming current, I2 is the outgoing current. Sum of incoming currents IY plus I1 is equal to outgoing current I2. Thus, IY is equal to I2 minus I1. Substitute the values of I2, I1, subtract, you get this one. Convert this rectangular into polar form, you get this. Similarly, how to find IB? IB is this line current. Apply KCL at this point. Incoming current is IB and I2. Outgoing current is I3. Applying KCL, sum of incoming currents IB plus I2 is equal to the outgoing current I3. Thus, IB can be found by using I3 minus I2. Substitute the values of I3, I2, subtract, you get IB. Thus, the line current values are IR 13.53 ampere, IY 8.42 ampere, IB 21.51 ampere. Finally, when you give the answer, you have to give the answer in polar form. Next problem. A delta load with ZAB 10 angle 30 degree, ZBC 25 angle 0 degree and ZCA 20 angle minus 30 degree is connected to a 3-phase 500 volt ABC system. Find the line currents and the total power. This is the problem given. Let the phase sequence be ABC. If the phase sequence is ABC, A, B and C, then the voltage is EAB is 500 angle 0 degree. Next, EBC. EBC is 500 angle minus 120. Next, ECA. ECA is 500 angle minus 240, or it is equal to 500 angle plus 120 degree. First, calculate the phase currents. IAB is equal to phase voltage EAB divided by phase impedance ZAB. EAB 500 angle 0 degree. ZAB is 10 angle 30 degree. It's given in the problem. ZAB 10 angle 30 degree. Thus, it is equal to 50 angle minus 30. Similarly, we can find IBC and ICA. Thus, we have found the phase currents IAB, IBC and ICA. How to find the line currents? From the figure, IAB, IBC, ICA are the phase currents. IA, IB and IC are the line currents. We have to find the line currents IA, IB, IC by using Kirchhoff's current law. IA is equal to IAB minus ICA. So this is the value of IA. Similarly, the values of IB and IC can be found. How to find the total power? Total power is power in ZAB plus power in ZBC plus power in ZCA. We know the formula for power. Power in a single phase is voltage multiplied by current into cos phi. As I said, when we calculate the power, we have to take only the magnitudes of voltages and currents. Power in ZAB is this. Power in ZBC is EBC, IBC, cos phi BC. Similarly, power in ZCA is this one. Substitute the values. Thus, we get the total active power in the circuit is 42,476 watt. We can use another formula for finding the total power. That is, total power is sum of power dissipated in all three resistors. Power P is equal to I square, IAB square RAB plus IBC square into RBC plus ICA square RCA. We can use either this formula or this one. Thank you.